All right, recording is rolling. It is Wednesday, December 7th. So I'm going to do review questions with you guys today. You guys know there's a quiz tomorrow on rotational dynamics. So it could be on anything. Remember again, guys, all these notes. Well, actually, I hadn't made this one at this point, but we went over this too. You guys did a lab for a couple of days. That was this, right? Okay, so we did a lab yesterday involved rotational inertia. There's a bunch of stuff about torque, angular momentum, right? All these things, right? So, we've got some. There's also rotational kinematic motion. Right? You guys remember these equations? Right, this relationship right, with the turntable, so put a point on the outside edge, right? Like how far is it moved, or how far is the turntable rotated? Where's the coin located? Kind of thing, right? And so, and that might show up. I'll pick up you guys' puzzles tomorrow because here, this will be open notes, right? So this quiz is going to be open notes tomorrow. Okay. Now, of course, that doesn't mean you don't want to study and practice. We'll do some exercises today, right? But because you don't want to say, oh yeah, I kind of remember that vaguely from like a week and a half ago, right? So we'll do some practice today. Right, so you guys can use your puzzles as part of your notes tomorrow if you want to do that. And we'll start the midterm review on Friday. Right. Before we do some practice problems, one other thing, switch my screen here. And I just got in my email. Next week is a Spirit Week. I did post this to Google Classroom. So see, Monday is holiday hats and socks. Tuesday, tacky holiday gear. Wednesday, Santa versus Grinch, either red or green. Thursday, holiday character day. And Friday is pajama day. There you go. All right. So let's start with some rotational kinematics. How about that? Rotational kinematics. Suppose suppose it gives this thing a spin. And it's actually let's get an estimate for this. Looks like it's going about let's call it 1 revolution a second, I guess. 1 revolution a second. And it slows to a stop in could that have been maybe I don't know 9 seconds, I'll call it. Okay. So let's say it's starting at 1 revolution per second and slowed to a stop in 9 seconds. Let's figure out everything about that motion just given those starting values. So let's say omega initial was 1 revolution per second, right? 1 revolution per second. I told you guys that the time was 9 seconds, okay? And it came to a stop. Okay, so what's we've got these 5 kinematic variables going around, right? Okay, angular displacement, angular velocity, initial and final. Some amount of time, and the angular acceleration, like the rate it could slow down. Okay, this is one of those posters hanging from the ceiling, like right up there. Right, so you guys can reference this if you need to. Okay, so you guys saw that turntable slow to a stop. What's another, based on all this, what's another kinematic variable that you guys know? How about this? If it slows to a stop, what is the final angular velocity? 0. 0 what? What's the unit for that? Should we do radians per second? Okay. You can say revolutions per second, radians per second. You can say degrees per second. Okay. Ooh, should I convert this initial angular velocity to radians per second? Okay. I bet I should if I'm going to be using those kinematic formulas. Right? Shouldn't you always, anything you're popping into those 3 kinematic formulas, having like radians per second? Okay. You guys remember dimensional analysis? Dimensional analysis? How do you go from revolutions to radians? What's the conversion? How many radians in 1 revolution? Yeah, 2 pi. Kind of like circumference equals 2 pi r, right? It's related to that. Right. Oh, look at that, radians per second. So I'll call that 2 pi radians per second. Oh, thank you. Right. Right, so still 2 things we can solve for. You can solve for how far did it turn theta and what rate was it slowing down alpha. Now, which of those is probably the best one to solve next? You guys want to solve for alpha first or theta first?
Alpha.
Alpha. Yeah. Here's why. Because alpha is in all three of these equations, so you got to have it to be able to solve anything. And if you don't have it, well, you don't want to pick an equation that has two unknowns in it. Right? I guess you could set up a fancy system of equations, but that would take a long time to solve. Right? So I like this middle one right here because you know three of these four variables, don't you? Right? You solve for this alpha, knowing these three guys right here. Right? So let's do that. Let's go. By the way, all day today, see if you guys can stay a step or two ahead of me because I'm solving these with you guys, but I'm trying to do it kind of slowly so that you guys can beat me to the answer. Right? If you always know what the next step is going to be, then that's a good sign that you're in good shape for tomorrow. Right? So we're doing rotational kinematic motion. You know, this guy is 0. This guy is, or whoops, sorry, whoops, wrong way. Okay. This guy's 2 pi radians per second. Oops. This guy's 0 rad per second. Plus did you guys get that right there? Okay. You guys get that? Okay. Now that's just the rate it's slowing down. Okay. So far we've got bam, 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 bam. That's 4 of the 5 kinematic variables. So the last one we got to solve for is how far did it turn? Right? Okay. Trying to give you guys a head start. You guys, of course, have this poster hanging from the ceiling, kind of that yellow beige color. It's right there. Can you guys solve for how far did that rotate? How far did it rotate? So I bet a lot of you guys already on your paper have this written down. Or you could use the third kinematic formula. That'd be fine too. But this one you don't have to do any algebra. You can just all arithmetic. You can just plug numbers in. How far did it turn? That's what theta is, right? How far did it turn? And radians. Okay. So it was going at 2 pi radians per second. 2 pi radians per second. Okay. It took 9 seconds to slow to a stop. And it was slowing down at negative 0.7 radians per second per passing second. Nine seconds shows up again, square that. Okay. This should tell me how far this rotated while it was slowing to a stop. Okay. You guys get that about? Rounding a little bit. You guys got that? Yeah. Hey, you know what? I remember when I started out, I gave you guys initial angular velocity in revolutions per second. So it was about 1 revolution per second. Can you guys convert that back into revolutions? Maybe I want to know like how many total rotations did it make? And I'm trying to go a little bit slow so you guys can beat me to the answer. There are this many radians for 1 revolution. In your calculator, you put that in parentheses to group it together so that it's all in the denominator. You guys get, yeah, you guys get about 4.5. I don't think that last digit is really that precise, but I think if you kept the pi all the way through, but it should be about 4.5, right? About 4.5 revolutions. All right.
You just divide it by 2 pi or...
Yeah. Now, if you do this, if you do 28 divided by 2 pi like that, then it'll give you the wrong answer.
Yeah, that's what I.
Okay, so the way the calculator is interpreting that is it's dividing by 2 and it's turning around and multiplying by pi. So what you have to do is group the 2 pi in parentheses. And then it'll give you the correct answer. There you go, about 4.5 revolutions. Can you guys make a graph for what we just did? Actually, let's do a set of graphs. You guys remember kinematic motion? We traditionally make like 3 graphs. Okay. Got displacement, velocity, and acceleration all versus time. Let's do a set of graphs for that scenario. Displacement versus time, velocity versus time, acceleration versus time. Except these will all be angular values. So the angular displacement in radians versus time in seconds. Angular velocity, radians per second, time in seconds. Angular acceleration, radians per second squared, time in seconds. Okay. Okay. So the same story that we just did. Here's your origin point on all 3 of these. I won't give you guys this point right here. I'll say that you start keeping track. So angular displacement, I'll give you guys that point. Right? But everything else, can you guys draw the basic shapes for what we just did? I just know it was 9 seconds it took to come to a stop. What do those graphs look like? Give you guys a head start. Now, how I usually go over this story with you guys is I start with the middle graph and then branch out from there because all these 3 graphs are related to each other. Okay. So remember, it was originally going 2 pi radians per second. So that's about 6.28 radians per second. So this is definitely a point on this graph. And then at the 9-second mark, it slowed down all the way to 0 radians per second. Okay. And in this class, we always assume that it slows down uniformly. So that's that graph right there, right? You guys got that for the middle graph? This is like the spin rate per time, right? Angular velocity versus time, radians per second. Okay. 30 seconds. So it was going really fast and slowed down to stop after 9 seconds. How about angular acceleration versus time? What's that graph going to look like? Ah, there you go. Continuous negative. Bam. Ooh, I bet we can attach a number to this. What number goes right here? There you go. Negative 0.70 radians per second squared. Right? It's slowing down uniformly the entire time. Okay. All right. Last one, angular displacement versus time. Okay. What's that graph going to look like? All right. How about this? What if you break this into like 3 seconds, 3 seconds, 3 seconds? It goes 3, 6, 9 seconds, right? Guys, what property of omega versus t tells you theta? Area. Ah, okay. Because radians per second multiplied by seconds brings you back to radians, which describes how far did it turn. Okay. You guys see during the first 3 seconds, it turned big wedge right there. So 3, 6, 9 seconds. Turn a long way during the first 3 seconds. Then between 3 and 6 seconds, it picked up some more, but it was like slowing down. So that didn't actually turn as far. It's like slowing down, right? So yeah, still gaining positive angular displacement, but not as much. And then, ooh, these last 3 seconds where it slows to a stop, it's still turning, right? Still gaining positive angular displacement, but hardly any at all. Okay. And what shape is this called? A parabola, right? Is that part of a parabola? Okay. And right where it comes to 0 here at the 9-second mark, or the 0 angular velocity. Okay. What property of this parabola is that called? Vertex. Ah, that's the vertex of the parabola right there, isn't it? Okay. So like if you kept going, if it like slow down and then turned around and start speeding up the other way, like it continue this like this, and this parabola goes upside down. Okay. But it just stops, and that's the whole story right there. So we were just saying that here, I was hatching in this area underneath omega versus t, and we said that must be theta, right? Like how far, really, it's like the change in theta, it's like the acquired angular displacement. But if you started at 0, then it just tell you what theta is. Okay. Okay. There's another property of this graph that also represents something. How about the slope of this graph? What does the slope of omega versus time tell you? Yeah, angular acceleration. See how it's like a negative slope? Ah, because this is a negative coordinate. Negative slope, negative coordinate. That's it. So that is negative 0.70 radians per second per passing second, but radians per second squared. Right? Right? You guys remember this? Okay, so there's some rotational kinematics. Right, let's do some torque. Torque stuff. Do a few torque problems. Right? Oh, you guys did a torque lab over 2 days. And remember I told you guys initially that one of the inspirations for the torque lab was what if you have like some unknown mass, right? So one known, one unknown, okay? And you set up a balance beam, so you have a pivot. So this is all balanced out. Okay? I can like balance these like this. Okay? Now if they're equidistant from this pivot point, does that mean that they're the same mass if it's all balanced? Yeah, same mass, same weight, same torque, right? Got like a counterclockwise torque and a clockwise torque relative to this pivot point. Okay? Those are balancing out. Okay? What if the distances are different? Which one of these would be heavier? Suppose this was balanced, just ignore the fact of what these actually are. Suppose that was balanced right there. Which one of these would be heavier? The one on the left or one on the right?
Heavier or more important?
Like heavier, like more mass, more weight.
The one with the higher mass?
I'm thinking this guy would have to be heavier if they were balanced right here, right? Because a huge weight crossed with a small radon. So this very small r crossed with a huge force is equal to this very large radius crossed with a small force. Right? That would balance out. Counterclockwise torque, clockwise torque. You guys see that? Right. And then vice versa. Suppose like that was balanced. Well, now this guy would have to be really heavy, and this guy would have to be really light to balance that seesaw. Is that? Here, let me get a picture going for exactly what I've just been talking about. Suppose you have a seesaw. Here's the fulcrum, middle of the seesaw. Okay. I got a couple of friends. This guy and this guy. Call this guy Alan and this guy Bob. How about that? Okay. And I know Alan, I'll say mass of Alan is like, call this guy 40 kilograms. He's like a little kid. Okay. And he's sitting, let's say 3 meters from the fulcrum of the seesaw. Okay. And he's got a friend with him. And this friend is sitting 1.5 meters away from this pivot point. Okay. Now, from our point of view, isn't Alan causing a counterclockwise torque relative to this pivot point, and Bob is causing a clockwise torque? Suppose those are exactly balanced out. So they balance out the seesaw. Who can tell me how massive is Bob? How much mass does Bob have? How massive is Bob? So you guys know the principle here is that the torque zeroes out,
Yeah.
right? So you guys treating this pivot as like the door hinge, right? And you guys know torque is R cross F, right? How massive is Bob? Who's gonna get this? You guys are doing some version of this. You've probably written down by now. Yeah. What you got?
Is it 80 kilograms?
Yeah, Ryan got. Yeah, 80 kilograms, 80 kilograms. Okay. So, here's a, I'm gonna say the sum of the torque goes to 0. So the torque caused by Alan and the torque caused by Bob are, well, the same absolute value, just one's positive, one's negative. Okay, we got counterclockwise and clockwise. So I'll say like this: the torque caused by Alan, absolute value, equals torque caused by Bob, absolute value. Right? One's counterclockwise, one's clockwise. They have to be the same, right? Same magnitude. And torque is R cross F. So I got radius Alan crossed with, now the force caused by Alan, isn't that his weight, M times G? Yeah, equals radius Bob crossed with mass of Bob times gravity field, right? Weight of Bob. Still doing absolute value, right? Okay. I said that. Okay. All right. Do you see what's going to cancel out? The G. Okay. So if you took this whole seesaw set to Mars, you would still get the same answer. Right? It doesn't matter what planet this is on. Right? Take this to the moon. These guys still have to be seated at those locations. Okay? So, hey, I know 3 of these 4 things. Talk for this guy right here. Also the fact that the radius is horizontal and their weight is vertical. Those are perpendicular to each other. So I don't have to worry about sine of theta, because sine of 90 degrees is just 1. So that's okay. So this guy's sitting 3 meters out, 3 meters. Has a mass of 40 kilograms. This guy's sitting half the distance out. Now it's to the right, so like negative, negative, drop the negative. So what's this guy's mass? We cut through some negative signs with the absolute value, but you guys get the idea, right? Okay. If you divide this 1.5 meters over, the meters cancels. 3 over 1.5, is that a ratio of 2 to 1? 2 times 40, is that 80? The kilograms is the mass of Bob. Okay. And the big picture principle is, guys, if Alan has to sit twice as far out from the pivot point as Bob to balance this thing, that means that Bob must have twice the weight and therefore twice the mass, right? It's all 2 to 1 ratios. Yeah, you guys said. You guys good there? Okay. Let's do a real basic torque one. Okay. Suppose I got a wrench. Nut right here. Okay. Maybe it's all rusted over. I'm trying to break the rust. I'm like pop, pop, pop. Okay. You guys know I can maximize the torque by checking 3 things. I want to push as hard as I can, counterclockwise. Okay. Push as hard as I can. Okay. Also, do I want to push here or do I want to push here? Yeah, at the far end point. So I want to maximize this radial distance. And also, do I want to push kind of this direction, like 45 degrees or at 90 degrees? Like 90 degrees, right? So there's 3 things you do. Maximize that R, maximize this force, make sure these are at 90 degrees to each other. Okay. Let's type some numbers to this. Let's say that this radius is like 30 centimeters, which by the way is approximately the length of your ruler. Okay. And let's have this force being like about 10 newtons, which by the way is the weight of your largest lab weight. How much torque is on that nut? How much torque? Yeah. Yeah. It's here in 300 Newton centimeters, right? Okay. So 30 centimeters crossed with 10 newtons is 300 Newton centimeters. You can say that. Hey, what if you wanted this in base SI units? Can you guys do Newton meters? How many Newton meters is that? 3. Yeah, 3. 3 Newton meters. So those are both valid answers, right? Okay. Either of those could be a multiple choice answer. You guys can do that? What about this? I get the same picture going on. I'm going to change one little thing. Okay, so I'll have the same length wrench. Let's go out. R equals 30 centimeters. Okay. I'll use the same force, 10 newtons, but I'm going to push at this weird angle. So force equals 10 newtons. Okay. And let's say that this angle right here is 160 degrees. 160 degrees. Okay. Now how much torque? Hey, if that's 160 degrees, how many degrees is this right here? Yeah, 20 degrees, right? Do you think you could play off either one of those and get the torque? I bet sine of 160 is equal to sine of 20 degrees. Sine of 160 degrees, sine of 20 degrees, I bet they're the same thing. Oh yeah, so you had said about 102, 103 Newton centimeters. All right, sounds about right. So we got 30 centimeters, 10 newtons of force, which by itself would be 300 Newton centimeters, because that's what we did last time. That's like the maximum torque you can get. But what if you push that funky angle? So sine of 160 degrees. Let's try this out. I did 300 sine 20 got 102.6, but what if I plug in 160 for the angle instead? Get the exact same thing. Okay. So that is 100 and, well, call it 103, how about that, Newton centimeters. Okay. So that's about a third of the torque that you could have gotten if you were, pressing at right angles. Okay. You guys can do that? How about actually? How about this? Day 2 of your guys' torque lab. I remember we had a meter stick. Here. All right. You were holding this up with a couple of spring scales, and you put a weight in the middle. I'm gonna simplify this a little bit from even from your lab. I'm gonna put how about one spring scale right here. So it's like a spring scale, right? And then another spring scale at the far end. So let's have a 100 centimeter long meter stick. Got some spring scales. Took there and there. Okay. And I'm gonna put a weight. Let's see. How about at the 80 centimeter mark? And let's do a really big weight. Let's do a crazy big weight. Let's have this guy be 100 newtons of weight, 100 newtons, which is like yeah, like 10 of these, right? Yeah, so 10 kilograms, about 100 newtons. And this is a meter stick. So you guys know this is like 0 centimeters here, and this mark is like 100 centimeters right here. I want to know, what is the force rating in each spring scale? What's the force rating in each spring scale?
80 centimeters?
Is it how much?
80 centimeters from 0?
Yeah, it's at the 80 centimeter mark. So this is 80 centimeters right here.
And how many is it?
Huh? Yeah, how much?
20 on the far side, 80 on the 100.
You're saying 20 newtons and 80 newtons?
Yes.
Yeah, I like that answer too. Okay. So the kind of quick way to do it is that the sum of the forces up has to be the sum of the forces down. So they have to add up to 100, right? 20 and 80 newtons do add up to 100 newtons. Okay. And also, however far over proportionally it is equal to how far the one that's closer to proportionally carries the total weight. So the fact that it's 80% the way over, this guy's going to carry 80% of the full weight. Okay. Now this is kind of a shortcut method. The proper way to do it, suppose I change this up on you guys by tomorrow, right, is to pick a point as the pivot point. Right? Now you can pick any point as the pivot point, but I like either one of these as a location. Because if you were trying to solve for both of these forces, that would be two unknowns, right? Here, I'll call this guy F sub L and F sub R, right? The force on the left spring scale and the force on the right spring scale. Right? See, if that's two unknowns, and you pick your pivot point as being at the location of one of those unknown values, here's your pivot, then the force at that pivot point causes no torque about that pivot point, kind of like pushing on the door hinge, the door hinges. Okay? So from this point of view, treating this as the door hinge, I see that the weight is trying to turn this whole thing clockwise, and the right spring scale is pulling back everything counterclockwise. You see that? And those have to balance out, don't they? The sum of the torque is 0. Here's your conditions for equilibrium. The sum of the forces has to go to 0 newtons, in this case in the y direction, because they're all vertical forces. Okay. And the sum of the torque also has to be 0, that's 0 newton meters. Okay. There's your conditions for equilibrium. Isn't that true? Equilibrium. Forces go to 0, torque goes to 0. Okay. And if the torque goes to 0, then the magnitude of this one clockwise equals the magnitude of this one counterclockwise. Right? So let's go ahead and solve the rest of that then. Again, we're doing like the full proper way. Right? So I'll show you guys the shortcut way. Right? Now here's like the full proper way. Okay. So I'll say the torque caused by the weight plus the torque caused by the right spring scale goes to 0 Newton meters. I should put in a step before this. It said that, well, basically this right here. Sum of the torque is equal to 0. Okay, so start with the step that leads to this step. Okay, so the torque caused by the weight is equal to the negative of the torque caused by the right spring scale. Okay. Torque caused by weight. That's R weight F weight equals negative R right spring scale force right spring scale. Right, R cross F. Okay. Now, since the radial distances are always horizontal and the forces are always vertical, those are already perpendicular to each other. Okay, so sine of 90 degrees is just 1. Okay, in case you forgot that, sine of 90 degrees is 1. So I just keep what I have. Okay, R cross F. Okay. This distance is 80 centimeters, and the force is 100 newtons. Okay, is that exactly what that is? Hot, hot, right? Okay. Now on the other side, the full distance is 100 centimeters, and we're like solving for what is the force on the right side. Okay, so divide 100 centimeters down. Here's where that proportion pops out of the page, right? 80 divided by this 100 is like 8/10, 80% times 100 newtons gives you 80 newtons of force, and also there's a negative. What does that negative mean in this context? Yeah, it's the opposite direction of the weight. See, if the weight's down and I'm calling that a positive force, then the spring scale pulling up must be a negative force, which naturally comes out to be. Right? Or you could have done what I did before. I just said the absolute value of this equal to absolute value of that, and then solved it that way. And right, could have done that. Got 80 newtons. Okay. Right. And then the next thing is that, see, if you know that this is 80 newtons, you can go back to this other condition. The sum of the forces goes to 0. So you got 100 newtons down, 80 newtons up. So to restore that, it must be 20 newtons right here. So you got 20 newtons and 80 newtons. Okay. Okay. You guys see that? Okay. Any question? Any question? Yeah. Right, so you guys did good. How about got another torque question for you guys. Remember we gave this thing a spin and it slowed to a stop. Actually, let me go ahead and pull up those numbers, because that was first thing I asked you guys, we did some kinematic motion, right? Remember we were saying that there was an angular acceleration of like negative 0.7 radians per second squared. Right. So let's play out that. Let's go with that exact scenario. So get a turntable spin. Let's say it was going like 2 pi radians per second, just like before. Went to a stop, took 9 seconds, slow down. Right. So we've done all the kinematic stuff already. Okay. What I want to know is what is the frictional torque? Now, to know that, you have to know some other stuff. So I have to give you guys some more information. Right? Like you might have to know what is the mass of this thing. What is the mass? Let's come up with something. Here, you guys know that your heaviest lab weight is like a kilogram, right? You guys have an estimate what just the top of this turntable might be approximately? Maybe how many grams?
500 grams.
500? Yeah, let's go that. Let's go with 500 grams. Okay, right. So let's call this the top turntable that's turning like 500 grams, right? That's 0.5 kilograms, 0.5 kilograms, right? And let's say it's approximately a circle, like a disc shape, and it has some width to it too, right? Has some width to it. Okay. And this has a radius of, so what is this? I mean, it's actually an octagon, so it changed a little bit, but if it's a circle, I'll call it 15 centimeters. How about that? It's pretty close to 15 centimeters right there. Okay, so 15 centimeter radius, we'll call it. Okay. Can you guys put this all together and solve for the frictional torque that was slow into a stop? Right? So give you guys some values here. If you know that omega naught was 2 pi radians per second, that's 1 revolution per second. Omega final is 0 radians per second. The time interval was 9 seconds. Then you also know that alpha is equal to negative 0.70 radians per second squared. Right, that comes out of all this. Let's consistent with all that. Right? Okay. Let's say that the mass of the disk is equal to 0.50 kilograms. Let's give it a radial size of 15 centimeters. Is that called 0.15 meters? Okay, we're doing everything in base SI units. Just like yesterday, that lab, I know we had a bunch of tiny numbers yesterday on the lab, but we were doing everything in base SI units, right? And do you guys remember a moment of inertia for a disk? So suppose it's like a solid cylinder that's rotating. Yeah, 1/2 mr squared. Yeah, you guys remember this, right? That is what this is, right? It's just like if you flatten this, right, it's still spinning about the central axis, right? That's it, right there, 1/2 mr squared, right? So 1/2 mr squared. Let's go ahead and grab that. So 1/2 times this mass in kilograms. Oops. Times this radial size in meters squared. If you plug these numbers in, you're going to get 0.005625. That's a lot of digits. What's the unit for that? What's mass is in kilograms? Radius squared, that's meter squared. Is that kilogram meter squared? Is that true? Just like your guys' lab yesterday, the answer was in kilogram meter squared, wasn't it? Okay. All right, so question. What frictional torque brought the turntable to a stop? I bet it's a really small torque, and I'm thinking that because it took 9 seconds for this thing to slow to a stop. That means it was spinning pretty good. probably means not a whole lot of friction. All right, anybody got it? Here's a hint right here. That's a poster hanging in the back of my room, about in the middle of the ceiling. Ah, right. Who's gonna get this first? Anybody got it? Right. Here, point out some stuff to you guys. Okay. So there's like two perspectives on torque. There's R cross F, which this picture is kind of set up for. I mean, there was some frictional force, some like radial distance active, right? But here's the other perspective on torque: I times alpha. Ooh. Sometimes you can set this equal to this and solve for stuff. But hey, do you guys know what I is?
Yeah.
You guys know what alpha is?
Yeah.
Ah,
Good point. 0.0039.
all right. Yeah, Dylan got a 0.0039. That would be Newton meters, wouldn't it? Okay, just multiply those two together. Okay. Oh, and of course it'd be negative, but that aside, I guess the magnitude could do that, right? All right. So just do torque is equal to I times alpha. Okay, here's your I. Here's your alpha. And so this whole thing comes out to 0.0039 Newton meters of torque. So that turntable to a stop. You guys do that? All right, how about the ice skater question? Did the ice skater? You guys with the ice skater, right? Also, you guys remember Paul Hewitt hopped on a turntable and also did the same thing, right? He held some weights way out, went to a slow spin, and then pulled them in, went speed up spinning, and then he pulled them out again, went slow again. Then he pulled them in, went fast. You go back and forth. Okay. So, what if an ice skater starts spinning and starts out with the rotational inertia of let's pick up a crazy number. How about let's go 60 kilogram meters squared. I'll call it I naught. Okay. Let's have omega naught, like the initial angular velocity, be like 1 radian per second, right? It's about 57 degrees per second, right? About like this far per second. Probably spin about that fast, so pretty slow, right? And then maybe the pull their arms inward. Maybe this number plummets down to say I final, like the final state of like 20 kilogram meter squared. Okay. Who could tell me? 3. There you go. All right, you got it. Okay. Yeah, so Steven's saying 3 radians per second. Okay. Because here's the principle. L naught equals LF. This is angular momentum. So that's I naught omega naught equals I final omega final. Okay. So 60 times 1. This would be kilogram meters squared radians per second equals 20 times 3 kilogram meters squared radians per second. Just like that. Here you go. So if one decreases by a factor of 3, the other has to increase by a factor of 3. Okay? Is that true? You guys see that? Hey, which one of these, here's before, here's after, like pre and post, which one of this has more rotational kinetic energy? Yeah, this after one, right? there's a few ways you can get that. You guys know rotational kinetic energy is 1/2 I omega squared. Now, the fact that I times omega is conserved, right? One increases as much as the other decreases proportionally. Okay? But that omega squared, ooh. So if I goes down by a factor 3 and omega goes up by a factor 3, if you square that factor 3, then it's not a wash. Actually, it looks like kinetic energy is like 3 times as much after compared to before. If you run this and get the number of joules, but there's 3 times kinetic energy here compared to here. Okay. But wait a minute, where'd all that energy come from? I thought energy was conserved. Doesn't it take some effort to pull your arms in? So would you be doing force times distance, pull your arms in, which is adding in mechanical energy to the system. Okay, so it's coming from your muscles, like stored chemical energy, isn't it? Right. All right. So I think it's a pretty good review. I think you guys should be pretty good for the quiz tomorrow, especially if you felt really good about this review today.